Right, in chapter 11, there will be an assignment. So just write that down here. The assignment problems are 1, 5, and 9. Okay, so this 3, 1, 5, and 9. And I'm going to be solving number 7 and 8. So let's get started then with number 7. We have, once again, remember our production function is in this form. And the functional form that's given in number 7 is k to the power alpha n to the power 1 minus alpha, and it's given that alpha is equal to 1 by 3. So if we plug in that value, what we get is y is equal to k to the power 1 by 3 n to the power 1 minus 1 by 3, so 2 by 3. This is our production function. Okay. So part A, question is this production function characterized by constant return to scale? Okay. How do we do that? Constant returns to scale means that if we increase all the inputs x times, the output will also increase x times. So let's see what happens. Let's take x, any number, and we multiply k with x. 1 by 3, x times k, 2 by 3. So what we're doing is we're increasing, not k, n. So what we're doing is we're increasing both k and n x times. What does that give us? If we simplify this, this gives us x 1 by 3, k 1 by 3, x 2 by 3, n 2 by 3. And so this and this we can combine, and that becomes x to the power k 1 by 3, n 2 by 3. This much is y, right? So we end up with x times y. So what that means is that when all the resources are increased x times, the output y also increase x times. Therefore, the function that we have, y equals to k to the power 1 by 3 n to the power 2 by 3, is, or rather, exhibits constant returns to scale. Or in just to simplify things, yes. This function is characterized by CRS. That's part A. Part B. Are there decreasing returns to capital? Okay, this is an interesting question. So when we're talking about constant returns to scale, we're talking about increasing all the inputs, both k and n. But what if we increased only k? What happens then? Well, let's figure that out. Suppose we increase k by x times once again. X can be 3, 4, 5, 6, any real number. So we're increasing k by x, but we're doing nothing to n. What will that give us? X to the power 1 by 3, k to the power 1 by 3, n to the power 2 by 3. So x to the power 1 by 3, y. So we increased capital by x times. As a result, output increased by how much? This much. By x 1 by 3 times. And of course, we know that x 1 by 3 is less than x. So therefore, there is decreasing return in capital, not the entire function, but just in capital. What does that mean? That means that if we double the capital stock and change nothing else, output will increase, but it won't double. It won't increase by 100%. Maybe it will increase by 40%, 50%, 60%, not 100%. So there is decreasing return in capital, just capital. Similarly, part C asks us, is there decreasing return to labor? So what you guys need to do, exactly same thing, but instead of increasing, multiplying x with k, do it with n, and then see what happens. So I'm leaving part C for you guys, and you will see that there is decreasing return. Part D, okay, transform the production function into relation between, okay. So per worker term. So we have this k1 by 3, n2 by 3. Now we want this to be in per worker terms, so we divide everything with n. K by n 1/3 and n by n 2/3. That gives us small y equals to small k to the power 1 by 3. This is just 1 to the power 2 by 3, which is just 1. So this is our production function in per worker term. Okay. And that's part D done. Part E. For a given savings and depreciation rate, give an expression for capital per worker in the steady state. Okay, interesting. Now, what we have seen in the chapter is that in the steady state, what do we need? We have two things that determine the steady state, right? It's one is depreciation, and the other is investment. We have seen this kt plus 1 minus kt is equal to, or correctly, s yt minus delta kt. And of course, we know what yt is. Sorry, not big Y, small y. We know what yt is. So I can just write s kt to the power 1 by 3 minus delta kt. This is kt plus 1 minus kt. And what we know is that as long as investment is more than depreciation, this is investment, this is depreciation. As long as investment is more than depreciation, capital stock is increasing. And when investment is less than depreciation, capital stock is decreasing. At the steady state, these are equal. SKT 1 by 3 is equal to delta KT. This is the steady state requirement. From here, if we simplify, what are we going to get? We get S by delta is equal to KT divided by KT 1 by 3. Further simplification, we get KT to the power 2 by 3 equals to S by delta, or KT is equal to S by delta to the power 3 by 2, right? And this is what we had to find in part E. We had to find an expression for capital per worker in the steady state. So this is our how much capital per worker the economy will have in the steady state. That was part E. Let's move on to part F. We have to find an expression for output per worker. Okay. Output per worker, of course, is this right here. This is output per worker. So YT is equal to KT to the power 1 by 3. Now we know what is KT, right? KT is S by delta, 3 to the power 2. This is KT to the power 1 by 3. So if we simplify, what we get is YT is equal to savings divided by depreciation rate to the power half. And this is output per worker in the steady state. That was F. Let's move on to part G. So now we have some values. Okay, so we have savings is 0.32. So that means we save 32% of our income. And we have delta equal to 0.08, which means annual depreciation rate is 8%. What do we have to find? Okay, we have to find the values of all this. Okay. KT then is how much? It's S by D to the power 3 by 2, which will be equal to 0.32 divided by 0.08 to the power 3 by 2. That's it. G. Am I doing it correctly? Solve the steady state level of output. Oh, output per worker. They haven't really asked for capital per worker. This is how you calculate it. You guys can just do it. But what the question asks for is output per worker, which is, of course, this equation right here. So S by delta to the power half. So that will be 0.32 by 0.08, 1 by 2. That is 2. That's it. So output per worker is 2. Each worker gives us 2 units of output. That's part G. Let's move on to part H now. Okay. So what has happened is that in the economy, there has been a change. Depreciation has stayed the same at 8%, but savings rate has halved from 32%. Now it's just 16%. And the question is, what is the new steady state output per worker? Same calculation. YT is equal to S by delta to the power half. So we have 0.16 by 0.08 to the power, which is 2 to the power half. So however much that is, you guys can use your calculator and find that out. It'll be 1.14 something, 1.41 something. That's it. That's the end of question 7. Let's move on to 8. We have the same equation in question 8. So y equals to k to the power 1 by 3, n to the power 2 by 3. Or if we move to the per worker term, y equals to k1 by 3. Okay. And what is given is that savings is 10%, depreciation is 10%. Okay. We have to find what is the steady state level of capital per worker, what is the steady state level of output per worker. We can do A and B together. Okay. Capital per worker, output per worker. Okay. So capital per worker is given by S by delta to the power 3 by 2. Now, of course, this equation will change depending on the production function. Because in 7 and 8 we have the same production function, we can use the same expression for capital per worker and output per worker. But of course, if this was different, then we would have to calculate this once again for capital per worker. In this instance, we don't have to. I mean, they're both 0.1, so 0.13 by 2, so we get 1. And same way, yt will come as 1. You guys can do the calculations. So what we see is that, let me write this down. In steady state, capital per worker is 1 and output per worker is 1. So effectively what that means is that we have given each worker 1 unit of capital to work with, and as a result, they are each producing 1 unit of output. Okay, that's part A and B. Part C. Okay, now what has happened is savings has stayed the same, but depreciation, which used to be 10%, has increased to 20%. Okay. And what will be the new levels of steady state capital per worker, output per worker? Okay, that's easy enough to calculate. Capital per worker is still 3 by 2. What we have now is savings is still 10%. Output is, depreciation is 20%. And so as a result, let me just get my calculator and see how much this is. We get 0.35, and output per worker is half, so 0.1 divided by 0.2, half. This gives us, see how much, 0.71. So because depreciation has increased, which means that the investment that we're making to create new capital is getting worn out much quicker at twice the rate. And as a result, in the steady state, remember this is just for the steady state, what's going to happen? The stock of capital and output is falling. You know, the question doesn't ask for it, but I'm going to draw the graphs of this because I think that will help us understand. Okay. So we have capital here, we have output here. So this is function of K. This is investment. We have depreciation. So what we had initially was that this was our steady state. So let's call this K star. This is where we were. And so we calculated and we saw that this was 1 and this was also 1. Then what happened was depreciation increased. Okay. Now think of this mathematically. What will happen if depreciation increases? What happens is that the line becomes steeper. This is with the new depreciation. Now see what has happened. Because we have higher depreciation, this now is our new steady state point. So let's call this K prime. this now is our new output, and we have already calculated their values. This is 0.35 and this is 0.71. Okay, now you guys have to realize that we were here at this point and then suddenly depreciation increased. That doesn't mean that we are going to immediately jump from, let's give them names. Let's call this A, let's call this B. We're not going to suddenly jump from A to B. There's going to be a transmission mechanism, a lag period. We're going to slowly travel from A to B. Every single year, our output per worker will fall a little bit. Our capital per worker will fall a little bit until we end up in the point B, which is of course our steady state. And once we've arrived at point B, we're not going to move anymore. Okay? So just like A used to be our steady state, now B is going to become a steady state. Okay. So let's see what's the next question. We've done C. D is compute the path of capital per worker. Okay. So what we are going to do now, so in year one, okay, in year one, we have KT1, YT1. Remember, we had already calculated them in part A and B. After this, depreciation changes, right? Depreciation used to be 0.1, then it becomes 0.2. As a result, things are going to start changing gradually. Let's take a look at year 2 now. We have KT1. What will be KT plus 1? How much capital will we have in year 2? That is given by 1 minus delta KT plus S YT. Remember, that's the formula. And so once again, if we get our calculators, well, let's fill this in first. 1 minus 0.2. KT is 1 plus S is 0.1 and YT is 1. Or what we can do is instead of YT, we're going to write YT is of course KT to the power 1 by 3. So we're going to do that. And if we use the calculator, how much do we get? 0.8, we get 0.9. If capital stock in year 2 is 0.9, then what will be output in year 2? Output will be, let's go back to the formula, which was KT plus 1 to the power 1 by 3. So 0.9 to the power 1 by 3. And that gives us 0.9 to the power 1 by 3, 9.66. 0.97. So this was for year 1. At the end of year 2, KT plus 1 is 0.9 and YT plus 1 is 0.97. Let's just keep them highlighted. End of year 1, year 2. Now we move on to year 3. Year 3, we're going to have KT plus 2 is equal to, once again, we'll use the same formula. So 1 minus depreciation times capital stock from previous year, which is right here. 0.9 plus savings rate, which is 10%, times capital stock from previous year to the power 1/3. Actually, we know it doesn't matter. So how much do we get? Calculator again. Plus three. That gives me 0.82. Okay. Output this year is equal to, plus 2. So that's of course kt plus 2 1/3. So 0.82 to the power 1/3, and that gives us and so we can keep calculating this, okay? So notice what is happening. We started off with capital per worker of 1. Then it came to 0.9. Then it became 0.82. And it's going to keep falling. It's going to keep falling until it reaches the new equilibrium level of 0.35. We're going down to that level, but gradually. Once again, look at what's happening to output. In year 1, we had output per worker of 1. Then it came down to 0.97. Then it came down to 0.94. So once again, this is going to continue falling. And output per worker is going to continue falling until it reaches 0.7. Okay, now I don't know how many years that's going to take. 5 years, 10 years, 20 years. But K and Y will continue to fall gradually from A to B. And once we reach B, there will be no more changes. That's the new steady state. Okay. All right, so that was part D, and that's it actually. That's all we're going to be doing from this chapter. Okay. So what I'm going to ask you all to do, of course, there's that assignment that you guys need to finish. Where did I write that down? Right here. So 1, 5, and 9 from this chapter. I mean, once I've done 7 and 8, so 9 will be pretty easy. Question 5 is also easy, and you guys know 1 is just true and false stuff. But what I am going to ask you guys to do is do number 7 and 8 on your own. After seeing this video, solve the problem yourself. And at each step, stop, and mathematically, this is not very difficult, slightly tricky, but not very difficult. But what's more important is for you guys to understand the economic implications and economic interpretation in each case. That's why I drew the diagram. I could have just done this mathematically, and that's pretty straightforward. But it's important for us to understand what's happening with the numbers that has implications for the economy. So do that, please. And that's it. So to summarize, chapter 10, 11, what we've done is we've talked about growth effectively. 10 and 11 has been all about growth and the question of where does growth come from. What we've done so far is we've taken a look at savings, we've taken a look at depreciation and all that. What we will be doing in the next 2 chapters, 12 and 13, is talk about technology. We have introduced technology. Remember what we did in the first chapter of medium run analysis, we introduced price into the model, but we did not let it vary. We assumed price was fixed, and then in subsequent chapters 8 and 9 we allowed price to vary. So we've done the exact same thing in 10 and 11. We've introduced technology here, but we haven't allowed technology to fluctuate. Technology has been assumed to remain fixed. Once you understand this setup, the framework that we're going to move ahead with, in chapter 12, we're going to allow technology to vary. And then in chapter 12, we're going to bring in short run and medium run, and we're going to introduce them into this model. And then we're going to have an overall idea of what's happening, what's going to happen to the economy when anything pretty much changes. Okay. All right. So that's it for these two chapters.